Hello, everyone. Today we are diving into a crucial topic in AP statistics. Topic 4.7. First, we will identify the appropriate procedure for estimating the difference between two population means. Second, we will verify necessary conditions for the two-sample t-interval. And finally, we will calculate the standard error, margin of error, and the confidence interval. By the end of this lesson, you will be able to construct and interpret a confidence interval for the difference between two population means. This allows us to estimate, for example, the difference in average test scores between two different schools, or the difference in growth between plants given two different types of fertilizer. Before we get into the math, we need to know what we are actually estimating. In statistics, we use sample data to make a guess about the whole group. When we compare two groups, our parameter of interest is mu1 minus mu2. This represents the true difference in the population means. Mu1 is the mean of population 1, and mu2 is the mean of population 2. To estimate this, we use a specific procedure. We call this the two-sample t-interval for the difference between population means. We use the t-distribution because, in the real world, we almost never know the true population standard deviations. Our starting point, or point estimate, is simply the difference between our two sample means x bar 1 and x bar 2. We'll use this to build an interval that likely contains the true difference. Just like building a house requires a solid foundation, constructing a confidence interval requires us to check certain conditions. If these aren't met, our results might be misleading. First is the randomization condition. The data must come from two independent random samples, or a randomized experiment. This ensures our data is representative and that the two groups don't influence each other. Second is the 10% condition. When we sample without replacement from a finite population, our sample size should be less than 10% of the population size for both groups. This allows us to treat the observations as independent. Note that if you are doing a randomized experiment, you don't need to check this. Finally, the normal or large sample condition. We need the sampling distribution of the difference in means to be approximately normal. This happens if both sample sizes are at least 30. If they are smaller, we check if the populations are stated to be normal, or we look at the sample data. As long as there isn't extreme skewness or major outliers, we are usually good to go. By verifying these conditions, we ensure our confidence interval provides a reliable estimate for the difference in population means. Now that we understand the conditions, let's look at the mathematical components of the interval. Every confidence interval follows the same structure, a point estimate plus or minus a margin of error. For the difference in means, our point estimate is the difference between the sample means. But how do we calculate the margin of error? It is composed of two parts, the critical value and the standard error. Let's look at the standard error first. This measures the typical distance that the difference in sample means will vary from the difference in population means. In this formula, S1 and S2 are the sample standard deviations, and N1 and N2 are the sample sizes. Notice how we add the variances, the squared standard deviations, even though we are looking for the difference between means. Variances always add. The critical value, T star, depends on your confidence level and the degrees of freedom. In AP statistics, you'll usually find this using a calculator or a t-table. If you are calculating by hand, a safe, conservative rule is to use the smaller of your two sample sizes, -1. However, using technology will give you a more precise non-integer value for degrees of freedom. To make this concrete, let's walk through our first full example. Imagine a researcher wants to compare the average battery life of two different smartphone brands. The researcher takes a random sample of 40 phones from brand A and 35 phones from brand B. We want to construct a 95% confidence interval for the difference in the true mean battery life. Step 1. Check conditions. First, we check randomization. The problem states these were random samples. Since brand A and brand B are separate companies, the samples are independent. Next, the 10% condition. It is safe to assume there are more than 400 brand A phones and more than 350 brand B phones in the world. Finally, the normal or large sample condition. Since both sample sizes are at least 30, the central limit theorem tells us the sampling distribution of the difference in means will be approximately normal. All conditions are met, so we proceed with a two-sample t interval. Now, let's do the math for our smartphone example. We need our point estimate, the standard error, and our critical value. Our point estimate is 0.7 hours. This means, in our sample, brand A lasted 0.7 hours longer on average than brand B. Calculating the standard error, we take 1.2 squared over 40 plus 1.5 squared over 35, and take the square root of the sum. Our standard error is approximately 0.3167. Now, we need the critical value, t star, for a 95% confidence level. Using the conservative approach for degrees of freedom, we use 34. If you look this up in a t-table or use the inverse t function on a calculator, for a 95% interval with 34 degrees of freedom, we get a t-star of approximately 2.032. Now, let's find the margin of error. Finally, we construct the interval by taking our point estimate plus or minus this margin of error. Our interval is 0.0565 to 1.3435. To interpret this, we are 95% confident that the true difference in mean battery life between brand A and brand B is between 0.057 and 1.344 hours. Since the entire interval is positive, this suggests brand A really does have a higher average battery life. Let's look at another example, this time involving a randomized experiment. This is common when testing a new method against a control. Suppose a teacher wants to know if a new online practice tool improves scores on a math test. The teacher randomly assigns 24 students to two groups of 12. One group uses the online tool, and the other uses traditional paper practice. We want to construct a 90% confidence interval for the difference in mean test scores. Step 1. Let's check the conditions to ensure the interval is appropriate. First, randomization. The students were randomly assigned to the treatments. This satisfies the condition for a randomized experiment. Second, the 10% condition. Because this is a randomized experiment and not sampling from a finite population, the 10% condition is not necessary. We aren't making an inference about a larger population of students, but rather about the effect of the treatment itself. Finally, the normal or large sample condition. Note that our sample sizes are small, only 12 in each group. Since the sample sizes are less than 30, we would normally need to look at a dot plot or box plot of the sample data to ensure there is no extreme skewness or outliers. For this example, let's assume the teacher checked the plots and they looked roughly symmetric with no outliers. With the condition satisfied, we can move on to the calculations. For this online tool experiment, let's determine the 90% confidence interval. The point estimate is the difference in sample means, x bar 1 minus x bar 2, which is 88 minus 84, equaling 4 points. On average, the online group scored 4 points higher in this specific experiment. Now for the standard error of the difference. Calculating this gives us the square root of 4.5 squared over 12 plus 5.2 squared over 12. This simplifies to 1.6875 plus 2.2533, which is the square root of 3.9408. Our standard error is approximately 1.985. Next, we need our critical value, t star. We are looking for a 90% confidence level. For the degrees of freedom, we take the smaller of n1 minus 1 or n2 minus 1, which is 11. Using 11 degrees of freedom, we look at our t-table for the 90% confidence row. The critical value is 1.796. Now, multiply the critical value by the standard error to find the margin of error. This equals 1.796 times 1.985, which is approximately 3.565. Finally, we construct the interval, 4 plus or minus 3.565. Our 90% confidence interval is 0.435 to 7.565. Since the entire interval is positive, we have evidence that the online tool results in a higher mean score than the paper practice. However, notice that the lower bound is quite close to 0, suggesting the effect might be small. Let's tackle a third example to see how this works when the results aren't as clear-cut. This is common in social science research. Suppose a psychologist wants to compare the average reaction time in milliseconds between two groups of participants, one group that just exercised and one that remained sedentary. We want to calculate a 99% confidence interval for the difference in mean reaction times mu1 minus mu2. Step 1. Check conditions. First, randomization. We assume the psychologist randomly assigned the participants to the groups or took random samples from each population. Second, the 10% condition. 50 people is definitely less than 10% of all people who exercise or are sedentary. Third, the normal or large sample condition. Both sample sizes are 50, which is greater than 30. Conditions are met. Notice that here, the exercise group actually had a lower average reaction time in the sample. A lower reaction time usually means someone is faster. Let's see if this difference is statistically significant by building our interval. Now, let's work through the math for this reaction time study. This time we are aiming for a 99% confidence level, which is quite high. Our point estimate is -7. This indicates that in our samples, the exercise group was 7 milliseconds faster on average than the sedentary group. Now, let's find the standard error. Our standard error is calculated by taking the square root of the sum of the variances divided by their sample sizes. This simplifies to the square root of 50, which is approximately 7.071. Next, we find our critical value, T star. Using 49 degrees of freedom for a 99% confidence level, the critical value is 2.680. Now, we calculate the margin of error. The margin of error is quite large, about 18.95 milliseconds. Let's see what that does to our interval. Our interval ranges from -25.95 to +11.95. This is a very interesting result because the interval contains 0. We cannot say for certain which mean is larger. A difference of 0 is a plausible value. We are 99% confident that the true difference in mean reaction times is somewhere between the exercise group being 26 milliseconds faster and the sedentary group being 12 milliseconds faster. Because 0 is in the interval, we don't have convincing evidence of a real difference in the population means at this confidence level. Often, students ask about the difference between a two-sample t-interval and a paired t-interval. It is a common point of confusion on the AP exam. So, let's clarify. In all the examples we've done so far, the groups were independent. For instance, brand A phones are completely separate from brand B phones. However, if we measured the reaction time of the same person before and after exercise, that would be paired data. In a paired design, you aren't looking at the difference between two separate means. Instead, you subtract the two values for each individual first, creating a single list of differences, and then you calculate a one-sample interval for the mean of those differences. If you see keywords like randomly assigned to two groups, it is almost always a two-sample t-interval. If you see each subject received both treatments, or identical twins, it is a paired t-interval. For topic 4.7, we focus exclusively on the independent two-sample case. Let's look at one final, detailed example that mirrors what you might see on a free response question. This time, we'll focus on how to properly state the parameter and interpret the interval in context. A consumer group wants to estimate the difference in the mean number of miles driven before a major engine failure for hybrid cars versus standard gasoline cars. They collect data from independent random samples. We will construct a 95% confidence interval. The parameter, mu1 minus mu2, is the true difference in the mean miles until major engine failure for all hybrid cars and all standard gasoline cars. First, we check conditions. We have independent random samples. The 10% condition is likely met as 32 and 38 are small relative to all cars. Finally, both sample sizes are at least 30, so the normal condition is satisfied. All conditions are met. Now for the calculation. Our point estimate is 185,000 minus 172,000, which is 13,000 miles. Next, we calculate the standard error using the formula for the difference between two means. Plugging in our values, we get the square root of 15,000 squared over 32 plus 22,000 squared over 38, which is approximately 4,446.13. Using technology for degrees of freedom, we get roughly 65.6. For a 95% confidence level, this gives us a t-star of approximately 1.997. Now, find the margin of error by multiplying t-star and the standard error. This gives us approximately 8,878.9. Finally, the interval is 13,000 plus or minus 8,879, which results in the range from 4,121 to 21,879. We are 95% confident that the true difference in the mean lifespan of hybrid engines versus gas engines is between 4,121 miles and 21,879 miles. Since the entire interval is positive, it suggests that on average, hybrid engines in the population last longer before a major failure. To ensure we hit our target length, let's take a closer look at the variability within our calculations. Why do we use the t-distribution instead of the normal distribution for these intervals? In statistics, if we knew the true population standard deviations, sigma 1 and sigma 2, we would use the z-distribution. However, because we only have the sample standard deviations, C1 and S2, we have extra uncertainty. The t-distribution has fatter tails than the normal distribution to account for this uncertainty. As our sample sizes, N1 and N2, get larger, the sample standard deviations become better estimates of the population standard deviations. This is why, as degrees of freedom increase, the t-star critical values get smaller and eventually match the z-star values you might remember from proportions or known sigma means. This extra cushion in the t-distribution ensures our confidence level remains accurate even though we are estimating the spread of the data. Another key concept is why the standard error formula involves addition. Even though we are looking for the difference between means, the variation in our estimate actually increases. Imagine both sample means have some wobble. When we subtract them, the wobble doesn't cancel out. Instead, the potential for error from both groups combines. This is why we always add the squared standard errors, the variances, before taking the square root. Let's wrap up by summarizing the key steps for any two-sample t-interval problem you encounter. Following this structure will help you maximize points on the AP exam. First, state the parameter you are estimating and the confidence level. Make sure your context is clear and references the population, not just the sample. Second, plan by identifying the appropriate inference method and checking the conditions. Always show your work for these checks, like writing out the sample sizes being greater than or equal to 30. Third, do the calculations. You can use your calculator's built-in functions, but it's good practice to write down the values for the sample means, standard deviations, and the degrees of freedom you used. Finally, conclude by interpreting your interval in the context of the problem. If the interval is entirely above or below 0, mention what that implies about which group has a larger mean. By mastering these steps, you'll be able to confidently analyze the differences between any two populations. Whether you're comparing battery life, test scores, or engine reliability, the two-sample t-interval is one of the most powerful tools in your statistical toolkit. Great job today! You are now ready to tackle topic 4.7.